You hear the phrase quantum entanglement and you think instant communication across the universe. Einstein called it spooky action at a distance. Pop science says particles talk faster than light. But here's the weird part. They're connected. They're correlated. Yet they can't send a single bit of information. Not 1 0, not 1 1. Nothing moves. The universe has handed us something that feels like telepathy, but works like a cosmic prank. So what can entanglement actually do? What are the limits no one tells you about? And why does the universe care so much about blocking faster than light messages? Let's crack this open. They publish one paper in Physical Review. May 15th, 2,500 words that will haunt physics for 90 years. The Einstein-Podolsky-Rosen paradox. They don't use the word entanglement. That comes from Erwin Schrödinger months later. But they nail the concept. Two particles. Measure one. Instantly know the other, no matter the distance. Einstein hates it. He calls it spooky. He says quantum mechanics must be incomplete. There must be hidden variables. Properties locked in at creation, like two coins in sealed envelopes. You open one, you see heads. Now you know the other is tails. Predetermined. No mystery. Einstein dies in 1955, still believing this. But the ghost of his objection sets up the next 60 years of experiments. Also comment from which city you're hearing this from. Also, this script is researched and factual using sources from Physical Review from 1935, where the original EPR paper was published, Nature from 2023, where the Google Quantum AI Surface Code results appeared, Science Advances from September 2025, showing the Kyoto University W state breakthrough, and the detailed Bell test archives maintained by University of Southampton Physics, showing the progression from Clauser-Friedman in 1972 through Aspect in 1982 to the Vienna loophole free test in 1998. Now back to the information. Physicist at CERN in Geneva. He's not trying to save Einstein, he's trying to test Einstein. Bell publishes a theorem, physics journal with the strangest name, Physics, Physique, Physica. Most people miss it. But Bell has done something no one thought possible. He's turned philosophy into math. He shows that if hidden variables exist, and if they're local, meaning no faster than light influence, then the correlations between entangled particles must obey an inequality. A mathematical limit, Bell's inequality. The universe has to pick. Either hidden variables exist and locality holds, which means the correlations stay weak, or quantum mechanics is right and the correlations break the inequality. You can test this in a lab. Bell dies in 1990, but his theorem becomes the most experimentally verified result in quantum physics. First real test of Bell's inequality. They use calcium atoms, excited by a deuterium arc lamp. The atoms decay through a cascade. 4p21, s0 to 4s4, p1p1 to 4s2, 1s0. 2 photons come out. Entangled in polarization, Clauser and Friedman measure correlations at different angles. The results violate Bell's inequality. Quantum mechanics wins. But there's a problem. The experimenters choose the measurement angles before the photons leave the source. Maybe information leaks, maybe the photons know what's coming. The locality loophole stays open. Institut d'optique théorique et appliquée. They close the locality loophole. How? They switch the polarizer angles while the photons are in flight. Acoustic optical switches, oscillating at 50 megahertz. The switch happens in less than 10 nanoseconds. Light takes 40 nanoseconds to travel 12 meters between detectors. No information can cross in time. The photons can't conspire. The results still violate Bell's inequality by 5 standard deviations. Aspect publishes in Physical Review letters. December 20th, 1982. The violation is clear, no hidden variables, no locality. One or both must go. Einstein's intuition was wrong. Geneva, Switzerland, Nicholas Gissen's team. They test entanglement over 10.9 kilometers of optical fiber. 2 photons, one goes north, one goes south. They measure correlations and arrival times. Bell violation confirmed. Distance doesn't matter. 2015, Ronald Hansen at Delft, first loophole-free Bell test. Detection loophole and locality loophole both closed simultaneously, using nitrogen vacancy centers in diamond, separation 1.3 kilometers. Published in Nature, October 29th. The violation persists. Quantum mechanics holds. The universe is fundamentally non-local, something Einstein refused to believe. They detect entanglement in top quarks. Published in Nature, heaviest known fundamental particles, mass 173 giga-electron volts, proton-proton collisions at 13 tera-electron volts, large hadron collider, second run. 2015 to 2018, They pick top quark pairs produced with low relative momentum, spins strongly entangled. They measure decay products, electrically charged leptons. Angular separation reveals spin correlation. Bell violation at the highest energy ever tested. Top quarks decay in 5 × 10⁻25 seconds. Faster than they can interact with environment. Entanglement survives. June 2024, Vienna. Philip Walther's team publishes in Science Advances. They measure Earth's rotation using entangled photons. A Sanac interferometer. Photons travel opposite directions around a loop. Earth's rotation shifts the interference pattern. Point 6, radian per second, matches the expected Sagnac effect to within experimental error. First demonstrations that entanglement can probe general relativistic effects. Rotation sensitivity pushed to new limits. Let's talk about what entanglement can do. Quantum cryptography. 1984, Charles Bennett and Gilles Brassard. BB-84 protocol. Use entangled photons to generate a secret key. Alice and Bob share pairs. They measure in random bases. If an eavesdropper intercepts the quantum state changes, Heisenberg uncertainty principle. You can't measure without disturbing. Alice and Bob compare a subset of their results over a public channel. If the error rate is too high, someone is listening. Abort the key. If error rate is low, the key is secure. First commercial quantum key distribution system. ID Quantique, Geneva, 2001. Now deployed in fiber networks in China, Europe, United States. The MICA satellite, launched August 2016. China, quantum communication over 1,200 kilometers. Ground station in Tibet, satellite in low Earth orbit. Entangled photons distributed, keys generated between stations separated by continents, published in Physical Review Letters, June 2017. No eavesdropping possible without detection. Information theoretic security. Not based on computational hardness, based on the laws of physics. Published in Physical Review Letters, March 29th. First experimental demonstration, 1997, Innsbruck, Austria, Anton Zeilinger's group, Nature. December 11th, single photon. Polarization state teleported across a lab bench. Entanglement required. Classical channel required. You need both. Here's how it works. Alice has a photon in an unknown state. She wants to send that state to Bob. They share an entangled pair. Alice performs a Bell state measurement on her original photon and her half of the entangled pair. This measurement destroys the original state, collapses the entanglement. Alice sends the measurement result to Bob over a classical channel. Phone line, radio, fiber. Doesn't matter. Bob uses that information to perform a unitary operation on his photon. His photon now has the original state. The state has teleported, but the classical message travels at light speed or slower. No faster than light communication. Molybdenum silicide. Detection efficiency above 80%. Time bin encoding. Success rate 25%, but it works. 2017. Mishis satellite. Jigang Ren's team. University of Science and Technology, China. Teleportation from ground to orbit, 500 to 1,400 kilometers, depending on satellite position. Published on ARC July 4th. Photon entanglement maintained across atmosphere. Tracking system keeps laser locked on satellite moving at 7.9 kilometers per second. State transferred. Fidelity above classical limit of 66.7%. University of Electronic Science and Technology, China. Guangzhou and Changzhou. Metropolitan Fiber Network. 7.1 qubits per second. Published in Light Science and Application. Superconducting nanowire single photon detectors. Near zero noise. High efficiency Bell state measurement. Teleportation fidelity 71%, above classical limit, real world conditions. Existing backbone network in Chengdu, no isolated fibers. This is infrastructure that carries internet traffic. December 2024, Northwestern University, Prem Kumar's team, quantum teleportation over 30 kilometers of fiber, while internet traffic flows through the same cable. Published in Optica, December 20th, Jordan Thomas. First author, classical communications, millions of photons. Quantum communications, single photons. They choose wavelengths carefully. Classical light at C-band 1530 to 1565 nanometers. Quantum light at O-band 1310 nanometers. Different channels. Minimal crosstalk. Photons don't drown in noise. Success rate uncertain, but the principle works. Quantum and classical networks can coexist. No need for dedicated infrastructure. Greenberger, Horn, Zeilinger states had entangled measurement for 25 years. W states did not. Multi-photon entanglement with different structure. Cyclic shift symmetry. The team built an optical quantum circuit. High stability. No active control needed. 3 photons in specific polarization states. Device distinguishes different W state types. Fidelity measurement shows correct identification. Why does this matter? Quantum teleportation can now handle more complex states. Multi-party entanglement, applications in quantum communication protocols, measurement-based quantum computing. This is cutting edge, published 2 months ago. Without it, quantum computers are just fancy random number generators. 2 qubits entangled, 4 possible states simultaneously. 3 qubits, 8 states, n qubits, 2 to the n states, exponential scaling. This is why quantum computers promise exponential speedup for specific problems. Shor's algorithm, factoring large integers. Published 1994, Peter Shor, AT and T-Bell Labs. A classical computer factors a 1024-bit number in centuries. A quantum computer with error correction could do it in hours. Grover's algorithm, database search, 1996. Love Grover, Bell Labs, quadratic speedup. Quantum simulation, studying molecular chemistry, drug design, material science. Entanglement lets you model quantum systems directly. Classical computers choke on 20 particles. Quantum computers handle hundreds. Decoherence. Entanglement is fragile. Photons from a light bulb, vibrations from a passing truck, cosmic rays from supernovae, thermal fluctuations at any temperature above absolute zero. All of these destroy entanglement. Qubits decohere. Superposition collapses. Entanglement breaks. Current superconducting qubits. Coherence time 1 to 4 milliseconds. IBM's systems. Google's Sycamore. 20 microseconds during the supremacy experiment in 2019. Each gate operation takes nanoseconds, so you get maybe 50 to a few thousand operations before decoherence kills the calculation. Trapped ion qubits last longer, seconds sometimes, but gate operations are slower. The race is always against the clock. Google Quantum AI, published in Nature, February 22nd. They demonstrate logical error suppression with surface code. Distance 3 qubit array, error rate 3.028%, distance 5 array. Error rate 2.91, 4%. Modest improvement. They need error rates below 1% to reach threshold. Below threshold means more qubits equals fewer errors. Above threshold means more qubits equals more errors and the system collapses. Google's result shows they're close, but not there yet. April 2024. Microsoft claims error rate with logical qubits, 800 times better than physical qubits, not independently verified at publication. Quantum error correction requires encoding 1 logical qubit into dozens or hundreds of physical qubits. Surface codes need roughly 1,000 physical qubits per logical qubit at current error rates. Want to run Shor's algorithm on a 2048-bit number? You need millions of physical qubits. No one has that. Not yet. January 2025. Riverlane report on quantum error correction. Global quantum funding $50 billion. Japan leads, $7.9 billion in 2025. United States, $7.7 billion. Real-time quantum error correction identified as crucial foundation. Error rates must drop from 1 in hundreds to 1 in millions. Megaquop regime, then billions, then trillions. Teraquop regime. Fault-tolerant quantum computers need all of this. The industry is racing. Companies like Riverlane build dedicated error correction hardware. Decoders that process 100 terabytes per second. Classical systems watching quantum systems in real time. Detecting errors, sending corrections. Before decoherence wins. This is the engineering challenge of the decade. Alice and Bob share entangled particles. Alice measures her particle in the up-down basis, gets up. Instantly Bob's particle is down, spooky action, but Bob doesn't know Alice measured. His particle looks random to him. 50-50 chance of up or down. He has to measure to see anything, and his results are random. Alice can't force a result. She can't encode a message. If she tries to manipulate her particle, the entanglement breaks. Bob still sees randomness. No information transfers. If Alice performs any operation on her particle, Bob's local statistics don't change. His marginal probabilities stay the same. He can't tell what Alice did without comparing results over a classical channel. Phone call, radio, fiber, all limited to light speed. Only when Alice and Bob compare data over that classical channel do they see correlations. Then they realize they were entangled, but the comparison requires classical communication. No way around it. Quantum entanglement plus classical channel equals quantum communication. But quantum entanglement alone equals nothing, just noise. Published in Nature, you cannot make a perfect copy of an unknown quantum state. Why does this block faster than light communication? Imagine Bob receives entangled particles. If he could clone them, he'd make many copies, measure half in one basis. Measure half in another, compare statistics. If Alice measured her particle, Bob's clones would show correlations. If Alice didn't measure, Bob's clones would show no correlations. Bob knows instantly whether Alice acted, faster than light signal. But cloning fails. The theorem says no. Any attempt to copy scrambles the state. Bob gets nothing useful. The universe protects causality. Nick Herbert proposed a faster-than-light device using cloning in 1981. Referees spotted the flaw, prompted the no cloning proof, published the next year. The loophole closed before it opened. September 2025. They argue the no communication theorem has hidden assumptions. Standard quantum observables. Hermitian operators. What if arrival time is an observable? Pauli proved in the 1950s that a naive time operator doesn't fit the framework. But labs measure time of flight every day. Mass, spectrometry, particle detectors. Maybe a new formalism allows time correlations that leak information. Das says Alice's measurement choice could affect Bob's arrival time histogram. Not position, not spin, time. If true, Bob sees the signal without classical channel. Faster than light communication. Maudlin says the no signaling arguments assume no dynamic influence. Circular reasoning. They claim experiments could test this in the next few years. Single particle arrival times, then entangled pairs. Either reinforce no communication or crack it open. Controversial. Mainstream physics says no. The community remains skeptical. But the mathematics is being worked out. We'll know soon. Quantum teleportation sounds like instant file transfer. It's not. Classical channel needed. Speed of light bottleneck. The quantum state transfers, but you need classical bits to complete the protocol. 2 bits per qubit teleported. Those bits travel classically. Phone line, radio, fiber, limited by relativity. Plus, the process is probabilistic. Bell state measurement succeeds only 25 to 50% of the time, depending on setup. Northwestern experiment. December 2024. No exact success rate published. NIST experiment. 2015. 25% at best. Then fidelity. How close is the teleported state to the original? Northwestern team 83% on average. Kyoto team 71%. Below 100% means information loss, noise, imperfect detectors. Decoherence during transmission, practical teleportation requires error correction, more overhead, more qubits, more complexity. Entanglement distribution over distance, loss in fiber, optical fiber absorption, 0.2 decibels per kilometer at 1550 nanometers. Over 100 kilometers, 99% of photons are lost. NIST experiment. Hiroki, Teksu. Only 1% of photons make it through. You need ultra-sensitive detectors, superconducting nanowires, cryogenic cooling. Even then, most attempts fail. Satellite links avoid fiber loss, free space propagation, but atmosphere scatters light. Clouds block transmission, tracking is hard, satellite moving at kilometers per second. Ground station must lock laser to milliradians accuracy. MISHIS does this, but it's expensive. Few countries can afford it. Scaling to global quantum internet requires quantum repeaters. Stations every 50 to 100 kilometers. Entangle segment by segment. Each repeater needs quantum memory. Store photons. Wait for confirmation. Then entangle next segment. Quantum memory barely works in labs. Solid state systems. Rare earth ions and crystals. Storage times, microseconds to milliseconds. Not enough for long-haul networks. Atomic ensembles and vapor cells. Seconds achievable. But integration with fiber is clunky. No commercial quantum repeater exists yet. 51 trapped ions. Entangled using spin exchange interactions. Squeezed quantum state. Measurement errors have, compared to unentangled ions, applied to optical atomic clocks. Improved accuracy. February 2025. Entanglement enhanced sensing demonstrated. Light squeezing. Reduced quantum noise in one variable at expense of another. LIGO gravitational wave detectors use this. Squeezed light injected into interferometer. Shot noise reduced. Sensitivity increased. Detected gravitational waves from merging black holes. September 2015. First direct observation. Entanglement was part of the toolkit. These applications work, but they don't send information. They measure physical quantities more precisely. No communication, no data transfer, just better sensors. Entangled photon pairs in Sagnac interferometer. Loop diameter unspecified, but lab scale. Earth rotation rate detected. Agreement with theory within error bars. Potential for improved gyroscopes. Navigation without GPS. Fundamental physics tests. Does general relativity hold in quantum regime? Entanglement probes the question, but again, no communication. No faster than light signaling, just measurement. Maybe detectors miss photons non-randomly. Biased sample violates fair sampling assumption. Closed by Ron Hansen, Delft, 2015. Detection efficiency 96%, high enough to trust results. Locality loophole. Maybe signal leaks between measurements. Closed by Alain Aspect, 1982. Switching during photon flight, freedom of choice loophole. Maybe experimenters' choices are predetermined. Alice and Bob think they choose randomly, but hidden variables set it up in advance. Hard to close. Requires random number generators driven by cosmic photons. Light from distant quasars. Decision made billions of years ago. Johann Rauch, Vienna. Anton Zeilinger, 2017. Published in Physical Review Letters, August 14th. Quasar photons 7.8 billion and 12.2 billion light years away. Used to set measurement angles, violation persists. No pre-existing conspiracy, unless it started before those quasars formed. Loophole effectively closed, superdeterminism remains. The idea that everything including experimenters is predetermined, untestable. Most physicists reject it. Bell violations stand. Photon 1 measured and destroyed. Photon 2 created later, never coexist. Yet correlations violate Bell inequality. How? Photon 1 entangled with photon 3, photon 3 stored, photon 3 later entangled with photon 4. Photon 4 measured. Photons 1 and 4 show correlation, but they lived at different times, entanglement swapping. The measurement outcomes correlate beyond classical limits. Does this mean entanglement transcends time? Interpretations differ. Some say entanglement is property of space-time, not objects. Others say causal structure permits backward influence in block universe. Elise Kroll, philosopher of physics, quoted in interviews, 2024. She argues space-time itself may be entangled if quantized. Quantum gravity theories need this, but unproven. Temporal entanglement experiments continue, testing limits, pushing boundaries, but still no faster than light communication. Causality preserved. Keys distributed using quantum photons. Encrypted communication between government and financial institutions. MISSIS satellite extends range globally. Europe, SECO QC project. Vienna, multiple nodes, fiber, and free space links. ID Quantique sells commercial systems. Banks use them, data centers, high security applications. Cost is high, equipment expensive, requires specialized training. But technology matures, prices drop. South Korea launches quantum network. 2020, United States, DARPA funds quantum internet research. NSF invests millions. 5-year plan to connect quantum computers across regions. Entanglement distribution between campuses. Harvard, MIT, Yale linked. Small scale. Proofs of concept. Full quantum internet decades away. Hope for useful results before decoherence. Variational quantum eigensolver. Chemistry simulations. Find ground state energy of molecules. Tested on small systems. Hydrogen molecule. Lithium hydride. Results match classical calculations. Not yet advantage. Quantum approximate optimization algorithm. Combinatorial problems. Graph coloring. Traveling salesman. Max cut. Results competitive with classical heuristics. Sometimes slightly better, usually not. Supremacy experiments. Google 2019. Sycamore processor. 53 qubits. Samples output of random quantum circuit. Task with no practical use. Claims classical computer would take 10,000 years. IBM disputes. Says classical simulation possible in 2.5 days with clever algorithm. Debate continues. Regardless, no useful application yet. China, Zhuchengzi processor. 66 qubits. 2021, claims faster sampling. Arms race and supremacy. Still waiting for quantum advantage on real problems. Drug discovery, protein folding, molecular docking. Quantum simulations predict binding affinities. Classical computers struggle beyond small molecules. Quantum computers handle hundreds of atoms in theory. In practice, noise kills accuracy. Need error correction, need more qubits, timeline uncertain. Optimists say 5 years, realists say 20. Pessimists say never unless fundamental breakthroughs. Elliptic curve cryptography vulnerable. Current internet security relies on hardness of factoring and discrete log problems. Quantum computer with millions of logical qubits running Shor's algorithm breaks these in hours. When does this happen? Estimates vary. Optimistic timeline, 2030. Conservative timeline, 2050 or later. National Institute of Standards and Technology, NIST, post-quantum cryptography competition, 2016 to 2022. New algorithms resistant to quantum attacks, lattice-based, code-based, multivariate, hash-based. Winners announced July 2022. Crystals, Kyber for encryption. Crystals, dilithium for signatures. Falcon, Sphinx, Plus, migration begins. Replace vulnerable algorithms. Update protocols. TLS, VPNs, blockchain. Takes years. Some entities already use post-quantum crypto. Governments, military, financial systems. Race between quantum computers and post-quantum defenses. Who wins? Unknown. Philosophical implications. What does entanglement mean? Copenhagen interpretation. Measurement collapses wave function. No definite state before measurement. Entanglement is correlation in wave function. Measurement on one particle affects global state. Appears non-local, but no signal. Many worlds interpretation. Hugh Everett, 1957. No collapse. Wave function always evolves unitarily. Measurement causes branching. Multiple worlds. In one world, Alice measures up. In another, down. Bob's particle is correlated in each branch. No single outcome. Entanglement is correlation across branches. Appears non-local within branch, but universe as whole is local. Pilot wave theory. David Bohm, 1952. Hidden variables exist. Particles have definite positions always, guided by wave function. Wave function is non-local. Instantaneous influence. Violates no signaling? No. Influences in configuration space. Not physical space. Can't use for communication. Consistent with Bell tests. But non-local. Einstein wouldn't like it. Threshold based on mass energy. Explains quantum to classical transition. Entanglement collapses when gravity becomes significant. Testable. Requires ultra-precise experiments. Not confirmed yet. Cubism. Quantum Bayesianism. Christopher Fuchs. Measurement updates agents' beliefs. Quantum states are subjective. Entanglement represents correlation in beliefs. No objective reality before measurement. Controversial. Many physicists reject. But consistent with experiments. Relational quantum mechanics. Carlo Rovelli. States are relative to observer. No absolute state. Entanglement is relative. Different observers see different correlations. Aligns with relativity. Space-time is relational. Why not quantum states? These interpretations agree on predictions. Differ on ontology. Experiments can't decide. Philosophy enters. Choose your interpretation. Results don't change. Black holes radiate. Hawking radiation. Temperature inversely proportional to mass. Black holes evaporate. Information inside lost. Violates unitarity. Quantum mechanics says information conserved. Contradiction. Entanglement, key to resolution. Firewall paradox. 2012. Almheri, Marolf Polchinski, Sully. AMPS. Entanglement between Hawking radiation and black hole interior causes firewall at horizon. Observer falling in burns. Contradicts equivalence principle. ER equals EPR conjecture. Einstein-Rosen bridge equals entangled particles. Juan Maldacena, Leonard Susskind. 2013. Wormholes and entanglement are same. Quantum entanglement stitches spacetime together. If true entanglement is geometric. Fundamental to structure of universe. Still speculative. No experimental test. But active research area. Entanglement entropy. Measure of entanglement in quantum field theory. Scales with boundary area, not volume. Holographic principle. Information in volume encoded on boundary. ADS-CFT correspondence. Gravity in anti-de Sitter space dual to conformal field theory on boundary. Entanglement structure matches geometric structure. Deep connection. Theoretical physics frontier. Real-world messiness. Entanglement in warm, wet biology? Unclear. Photosynthesis. Light harvesting complexes. Chromophores absorb photons. Energy transfers to reaction center. Quantum coherence observed. Oscillations in spectroscopy. Suggests entanglement helps efficiency. Prevents energy loss. But environment is warm. Room temperature. Noisy. Decoherence should kill coherence in femtoseconds. Yet experiments show nanosecond coherence. How? Maybe environment assists? Noise helps rather than hinders. Structured environment. Phonons tuned to electronic transitions. Research ongoing. Bird navigation. European robins sense magnetic field. Quantum compass. Cryptochrome proteins in retina. Radical pairs. Electron spins entangled. Magnetic field affects singlet-triplet transition. Changes chemical yield. Detected by bird brain. Experiments show birds disoriented by radio frequency fields. Disrupts radical pair mechanism. Entanglement in biology? Maybe. Speculative. Need more data. Quantum brain. Roger Penrose and Stuart Hameroff. Orchestrated objective reduction. Consciousness arises from quantum processes in microtubules. Entanglement across neurons. Collapses cause conscious moments. Widely criticized. Brain too warm, too noisy. Decoherence too fast. No experimental support. Mainstream neuroscience rejects it. But idea persists in popular imagination. Microsoft, Amazon, all have quantum computing divisions. Cloud access, IBM Quantum Experience. Anyone can run programs, educational, research, small scale. Google, Quantum AI. focus on error correction, Sycamore processor. Willow announced 2024, improved coherence, Microsoft, topological qubits, Azure Quantum, platform for multiple hardware backends, Amazon Bracket, access to IonQ, Rigetti, D-Wave, pay-per-use, startups, IonQ, trapped ion qubits. Public company, NASDAQ, Rigetti, superconducting qubits, PsiQuantum, photonic qubits, billion-dollar valuation, promises million-qubit system, timeline unknown, atom computing, neutral atom qubits, recent progress, scaling numbers. Investments pouring in, venture capital, government funding, hype versus reality. Gap remains large, but momentum real. Detect stealth aircraft, claimed by China, 2016. Doubts from Western experts. Physics unclear. Loss too high. Practical range limited. No confirmed deployment. Quantum imaging, ghost imaging, entangled photons, illuminate object with one. Detect with other. Image appears, low light conditions, useful? Maybe. Niche applications, quantum sensing for submarines, gravimeters, magnetometers, detect anomalies, underwater navigation, GPS denied environment, entanglement improves sensitivity. Research programs in US, UK, China, operational systems? Not yet, decade away minimum. Universe is non-local in correlations, but no faster than light signaling. No communication theorem holds, causality preserved. Entanglement enables new technologies. Quantum cryptography works today. Quantum teleportation demonstrated over 1,200 kilometers. Quantum computing in NISQ era. Useful applications soon? Maybe. Error correction scaling up. But decoherence is brutal. Fragile quantum states, milliseconds, and superconducting qubits. Environmental noise everywhere. Limits are real. No cloning. No FTL communication. Classical channel always required. Exponential overhead for error correction. Millions of physical qubits needed for useful computation. Technology advancing. Coherence times improving. Error rates dropping. $50 billion invested globally. Companies, governments, universities pushing hard. 5 years? 10? 20? Timeline uncertain. Entanglement remains spooky. Einstein was right to call it that. But he was wrong about hidden variables. Nature chose non-locality over realism. The universe correlates distant events. No mechanism, no signal, just math. And it works. University of Vienna rotates with entangled photons. Northwestern teleports through internet cable. Google refines surface code. Microsoft tests logical qubits. Riverlane builds error correction chips. Science pushes forward. Every month, new results. We're watching the quantum revolution in real time. Not revolution yet. Prelude. Proof of concept era. Demonstrating principles. Next decade critical. Will error correction work at scale? Will quantum advantage appear in real problems? Will post-quantum crypto deploy before quantum computers break RSA? These are open questions. No guarantees. But the physics is solid. Entanglement exists. It's weird. It's useful. And it's not going away. If you value deep research into verified quantum experiments like this, subscribe. Comment where you're watching from. This script pulls from Science Advances, showing W state entanglement breakthrough published September 12, 2025. Nature showing Google Quantum AI's logical qubit error suppression from February 2023 with measured error rates of 3.028 and 2.914%. Optica from December 20th, 2024. Showing Northwestern's internet cable teleportation by Kumar and Thomas, and the extensive Bell test literature archived by physics departments, including the Vienna loophole free experiment from 1998 published in Physical Review. Letters measuring violations over 1.3 kilometers with nitrogen vacancy centers in Diamond. Now, for the final piece. Collaboration with University of Science and Technology China, Hefei. They discover something unexpected. Noise helps quantum teleportation. Published in NPJ Quantum Information, May 11th, multipartite hybrid entanglement. Entangled different properties. Polarization and time bin. Normally noise destroys fidelity, but structured noise tuned correctly amplifies the signal. Fidelity approaches 90%. Chuanfeng Li from Hefei states this is significant proof of principle. Noise was always the enemy, now it's a tool. June 2024, same team, published again. Teleportation in noisy environments, fidelity near perfect. Classical intuition fails. Quantum mechanics permits counterintuitive solutions. This flips decades of assumptions. Error correction assumes noise is purely destructive. Fight it with redundancy. But what if noise helps? What if you engineer the environment, direct the decoherence, make it work for you? Early days, proof of concept only. But the door opens. Quantum technologies might not need perfect isolation, might function in room temperature. Might scale without cryogenics, maybe. The universe said no, the correlation just is. Measure here, result appears there, instantaneous in any frame, but unusable for communication. Why does the universe block FTL signaling so hard? Relativity, causality. If you send information faster than light, you can construct scenarios where effect precedes cause. Grandfather paradox, shoot a message into the past, change your own decision. Contradiction, universe prohibits it. How? No cloning theorem. No communication theorem. Wave function collapse mechanics. Marginal probabilities stay random. The math locks it down. No loopholes. Unless arrival time is an observable outside standard formalism. Das and Maudlin think, maybe. Mainstream says no, experiments will decide. But even if FTL communication opens, it won't be easy, won't be obvious, won't be a simple telegraph. You can't describe particle A without particle B, not even in principle. Measurement here is not local event, it's global update. The universe computes correlations across space, no delay. Information doesn't travel, the state vector evolves. Globally, instantly. In Hilbert space, not in physical space, that distinction saves relativity. Hilbert space is mathematical, infinite dimensional. Doesn't obey speed of light. Physical space does. Information in physical space can't move faster than light. State vector in Hilbert space updates instantly, but you can't access that update without measurement. Measurement couples Hilbert space to physical space. And measurement results transmit classically. Light speed limit restored. The universe is clever, non-local in correlations, local in causality. Cryptography unbreakable by computation. Sensors beyond shot noise limit. Computers that exploit superposition, simulations of quantum systems, chemistry, materials, drugs, problems intractable classically, accessible quantumly, maybe. If error correction works, if decoherence is managed, if scaling succeeds. These are big ifs, but the potential is real. Exponential speed up for specific problems, not all problems. Quantum computers won't replace laptops. They'll tackle specialized tasks, and entanglement is the engine. Without it, you have classical probability. With it, you have quantum interference. Amplitudes add, phases matter, wrong answers cancel, right answers reinforce. That's the magic. That's what Einstein called spooky. That's what we're learning to control. Final numbers, Atlas experiment. Top quarks at 13 tera-electron volts. September 2024. Michus satellite, 1,200 kilometers. June 2017. Northwestern, 30 kilometers through internet fiber. December 2024. Kyoto. W state measurement, September 2025. Google, error rate 2.914%, February 2023. Delft. Loophole-free Bell test, 1.3 kilometers, 2015, $50 billion global investment. 2025, 1 error per 100 operations today. Target 1 error per million, then billion, then trillion. Timeline uncertain. Coherence times, milliseconds in superconducting qubits, seconds in trapped ions, photons nearly infinite in vacuum, technology advancing, every year better, but gap between demo and deployment remains wide. Hype exceeds delivery, always has. Probably always will. But the physics is sound, the experiments work, the mathematics holds, and the universe keeps surprising us. Entanglement is real, spooky action at a distance. Einstein hated it, nature doesn't care. It's woven into quantum mechanics at the foundation. You can't pull it out. It's not a bug, it's a feature. The question is, what can we build with it? Correlation persists. Measure 1. Know the other, instantly, but can't signal, can't send message, can't communicate. Unless you include classical channel. Then you have quantum communication. Secure, powerful, limited by light speed. No FTL. No telepathy, no magic, just physics. Weird physics, non-intuitive physics, but testable, tested, confirmed. Thousands of experiments, decades of data, Nobel Prizes awarded, 2022, Alan Aspect, John Clauser, Anton Zeilinger, for experimental tests of Bell inequalities, for demonstrating entanglement, for pioneering quantum information science. The field matured, recognized, mainstream now, not fringe, central to modern physics. Entanglement drives the second quantum revolution. First revolution, transistors, lasers, GPS, nuclear power, built on quantum mechanics, but essentially classical in use. Second revolution, quantum information, quantum computation. Quantum cryptography, quantum sensing, leverage entanglement directly, exploit superposition, require quantum coherence. Different beast, harder, weirder, more powerful. Maybe. IBM launched Quantum Computing Cloud Access 2016. Google claimed supremacy 2019. China launched MISHIS 2016. Quantum networks in multiple countries. Startups funded. Billions invested. Practical applications? Quantum key distribution, yes. Used by banks, governments, secure communication. Quantum computing? Not yet. NISQ devices exist, run toy problems, demonstrate principles, show potential, but not quantum advantage on useful tasks, not proven. Maybe next 5 years, maybe 10, maybe 20. Depends on error correction, depends on scaling, depends on engineering breakthroughs. Science is one thing, engineering is another. Building million-qubit systems, stable, reliable, controllable. That's the challenge. Physics says it's possible. Engineering says it's hard. Economics says it's expensive. Politics says it's strategic. Quantum advantage, whoever gets there first. US, China, Europe. Race is on. National security implications. Economic implications. Scientific implications. Entanglement at the center. Spooky action turned into strategic resource. Einstein would be appalled and fascinated. Einstein asked, is quantum mechanics complete? Answer came back. Yes. Tested. Confirmed. Repeatedly. But the story didn't end. It expanded. Entanglement became tool, became technology, became foundation of new science. We're still unpacking implications, still discovering applications, still pushing boundaries. The universe gave us entanglement. We're learning what to do with it. Correlation without mechanism, connection without communication, influence without signal. It's the paradox Einstein identified. But it's not a paradox, it's reality. Math describes it, experiments confirm it, technology exploits it, and we keep probing. What else can entanglement do? What limits remain hidden? What applications haven't been imagined? The quantum revolution continues. Every year new results, every month new papers. September 2025. Kyoto cracks W states. Northwestern threads quantum through internet. Google refines error correction. Riverlane scales decoders. The field accelerates. Not hype, real progress, measured in error rates, coherence times, qubit counts, fidelity percentages, distance records, temperature requirements. The numbers improve. Slowly, steadily, the engineering gets harder as systems get bigger, but it gets done. Einstein's intuition could have been right. Particles could have carried definite values. No spooky action, no entanglement, classical correlations only. But Bell's inequality would hold, and Bell's inequality doesn't hold, violated in every test. By multiple standard deviations, across every platform, photons, atoms, ions, electrons, superconducting circuits, top quarks. Entanglement is universal. It's not platform specific. It's not an artifact. It's fundamental. And that tells us something deep. Reality at quantum scale is non-local. Relationships exist that defy spatial separation. The universe computes correlations globally. We live in quantum reality. Classical physics is emergent, approximate. Useful at human scales, but underneath entanglement weaves the fabric. We're learning to read that fabric, to pull threads, to weave new patterns. That's what quantum technology is. Applied entanglement, controlled spooky action. Engineered non-locality for communication, for computation, for sensing, for science. Einstein called it spooky, we call it quantum, and we're building the future with it.